Hello everyone, welcome back to the How series. We are beginning the workshop Programming and Optimization for Intel Architecture. This is session 3. Session 3 begins module 2, Expressing Parallelism, and we open this module with a discussion of automatic vectorization. Hopefully everybody attending is aware of the course web page by now. This is where you can download slides of my presentation, code of the exercises, watch video of all the presentations, and also ask questions in the chat. The chat window is at the very bottom of the course page, and you can ask questions as I speak during live presentations. We will handle the questions as they come in. If you have more extended questions, or if you want to ask questions after hours, feel free to use our forums. Here is the link. This is a hands-on workshop because we are providing everyone access to the Colfax cluster equipped with Intel Xeon processors, Intel Xeon 5 processors, and coprocessors. Access to the cluster is free, and you receive an invitation from this email address within an hour of registration. If you have not received your invitation, check the spam folder and email us if you don't find it still. You can use the cluster for the entire 2 weeks of the workshop, and the exact expiration date is stated in your invitation email. So let's talk about SIMD parallelism and vectorization. We will talk about vector instructions in Intel architecture. And as usual, I show this slide to emphasize that not only will we target different kinds of Intel architecture, but also that the material that I'm going to teach applies to non-Intel processors as well, as long as they support SIMD parallelism in the form of short vectors. We are going to try to learn vectorization, like all the other techniques, in such a way that you can apply modern code practices to your code and produce a single code base that will be portable across existing platforms and also scalable to future generations of Intel architectures. Let me illustrate first with a diagram what place vector processing takes in hardware. If you look at an Intel Xeon 5 processor, Knight's Landing architecture, inside of it you will find multiple cores. We have not talked about how to use these multiple cores yet, but be aware that there's up to 72 of them. The cores are organized into tiles of 2 cores, which is not relevant to this discussion, but explains why I'm showing 2 cores. What's important is inside the core, you have 2 vector arithmetic and logic units, ALUs. Each of these units is capable of performing short arithmetic instructions on short vectors. So there's the processor. Inside the processor are cores, and inside the cores are vector ALUs that apply a stream of instructions to short vectors. These vector instructions implement one of the forms of SIMD parallelism. SIMD stands for single instruction, multiple data. A SIMD processor can perform a single instruction to multiple data elements, but specifically a vector processor can load multiple scalar values into a short vector. There may be multiple short vectors if you have more than one operand for the current operation, and apply a vector operation, such as addition in this case, to all of these elements at once. The idea being that the latency and the throughput of this operation is the same as the latency and throughput of the corresponding scalar instruction. So if your vector width is 4, the potential speedup of your mathematics is 4x. If your vector width is 8, the potential speedup is 8x. If your vector width is 16, 16x, and so on. What exactly the vector width is depends on the architecture with which you're working and on your data type. In Intel architecture, vector processing made its appearance in 1997 with MMX instructions. MMX stands for Multimedia Extensions. And as the name suggests, they were only good for multimedia processing because they operated on integers and the vectors were pretty short, 64-bit wide. For scientific computing, vectorization became interesting with SSE and particularly with SSE2, which added support for floating point numbers, for standard operations such as additions, multiplications, division on 128-bit vectors. So let's do some math. 128 bits. How many 32-bit numbers can you fit? 4. This is single precision. If you're doing double precision, 128 divided by 64 is 2. This is double precision. So if you're doing double precision, like most applications performing scientific computing, your potential speedup is a factor of 2. And this is a considerable speedup. But on the other hand, if your application is complicated, then the idea of possibly refactoring it to get a factor of 2 speedup may not be appealing to a lot of people. So if you did not know about vectorization until this course, or if you have heard the word but don't know how it applies to you, you have a very good excuse. Until the early 2010s, the benefit of vectorization was just not significant enough to worry about it. But in 2011, with the Sandy Bridge architecture, Intel added support for AVX. AVX stands for Advanced Vector Extensions, I believe, and the width doubled to 226 bits. A later version, AVX2, also began supporting fuse multiply add, but now in double precision, your potential speedup is 4x. In single precision, the potential speedup is 8x because you can fit 4 double precision numbers into this short vector or 8 single precision numbers. With Xeon Phi in 2012, vectors became 512-bit wide, and now you can no longer ignore vectorization. So in double precision, the potential speedup is 8. In single precision, the potential speedup is 16. So if you are not using vectorization when you can, you're potentially losing more than an order of magnitude in performance. 512-bit vector extensions are not just for Xeon Phi. AVX 512, there's several modules of it. It will be used in future Xeon processors. For example, the Skylake architecture will support several modules of AVX 512. AVX 512 operates on 512-bit registers, and it has support for standard math. Also, it has modules with support for some transcendental functions, for complex memory accesses. And this instruction set is now supported by non-Intel compilers such as GCC. Older AVX2 instructions are supported by Xeons. They also have a wide range of instructions of operations that you can perform. But with this variety of vector instruction sets, how do we stand true to the promise of having a single code base for all platforms? Well, in part, this is because most Intel processors are backwards compatible with regards to vector instructions. For example, if you take a Knights Landing processor, latest second generation Xeon Phi, it supports its native AVX 512 instructions. But if you throw at it an executable with legacy instructions, they will still run. They will use only a fraction of the vector register. They will not run efficiently, but they will at least still run. Furthermore, AVX 512 is partitioned into 4 modules in the case of Xeon Phi: prefetch, exponential and reciprocal, conflict detection, and fundamentals, with the idea that some of these modules will be reused in future Xeon processors. So some code built for Knight's Landing is going to be reusable on future Xeons and vice versa. You can learn more about it in this publication on Clofax Research. So what I said is true, and it does help to maintain compatibility, code portability, and future-proofness. But the greatest portability and future-proofing comes from the usage of automatic vectorization. So we need to talk about how you can get vector instructions in your code. And I will explain two methods: automatic vectorization and explicit vectorization. With automatic vectorization, to get vector instructions in your code, you continue to write scalar code. So whether you use C, C++, or Fortran, your job as the programmer is to express your arithmetics in terms of loops that have certain properties allowing you to run multiple independent iterations of that loop at once. And this is the portable approach, because the compiler will take this code. It will lump together several values of I, and each iteration is going to be performed in its own vector lane, so multiple iterations will be performed at once in a short vector. To appreciate this even more, I will first illustrate explicit vectorization. Explicit vectorization, again as the name suggests, means that you are using direct access to the processor's features. It can be in the form of assembly, or in a more user-friendly format, in the form of intrinsic functions. Intrinsic functions are functions giving you direct access to processor instructions. They look like this. There's a prefix, the type of operation, the type of the data inside the short vector. There are special data types to hold your intermediate data, and there's a variety of instructions that you can crunch. I'm showing this to illustrate to you that the workflow of vector computation usually involves 3 or 4 operations. If you have data stored in memory, then the first order of business will be to load a piece of this data from memory into a vector register. This data lives in the memory or in a cache. The register lives on the core. If you have 2 operands, then step 2 is to load the second operand. When you have your operands in vector registers inside the core, you can call the vector addition instruction, and then inside the core you will produce a result. So the fourth operation will be to store this result back in memory or in a cache. In fact, this is the same workflow as for scalar computation, but it is particularly important to realize for vector calculations, because how you load and store data may be more important than how you do the math. Well, how exactly do you figure out which intrinsics to use? Well, you can look at your processor. In Linux, proc_cpu info will show you flags, and under flags you will find acronyms for all the instruction sets supported by your processor. Once you know the instruction set, you can go to the Intel Intrinsics Guide, which is a very interesting interactive page. It is really exciting. Even if you don't plan to use intrinsics, I recommend going there just to study what kind of intrinsics you have. For example, if you find that you are dealing with AVX 512 and you want to find something to do my favorite operation, vector addition, you can put the checks in the left-hand side, and there's all kinds of addition operations, well, let's sort them at least by add. A lot of addition operations. So which one do you need? You need to look at the prefix. It determines the type of the vector that you're dealing with, and you need to look at the suffix, which determines the type of the elements in that vector. For example, EPI 8 means that inside the vector are 8-bit integers. EPI 64 means that inside the vector are 64-bit integers. So let's find this one, PD. PD stands for packed double. So inside are 64-bit double precision floating point numbers. So this is what this instruction does. It adds a packed double precision floating point vector to another one. And actually, let's look at this one. And this is the pseudocode for this operation. Pretty straightforward. You need to be aware of masked versions of these instructions. They take the same arguments as regular instructions, plus a mask. A mask is a bit mask that allows you to use if statements inside the code. When the branch of the if statement is taken, meaning when the mask is set to 1, then inside that vector lane, you do the addition. Otherwise, you preserve the input. This allows you to vectorize loops with branches inside. Well, this is how you can figure out what intrinsics to use and how will it look in practice. I will demonstrate it once just to explain why it is difficult. Let's do numerical integration. This is the rectangle rule for integrating 1 over the square root of x from 0 to a. What I'm doing here is first I'm showing you the scalar loop. In the scalar loop, I compute delta x as a over n. This is it. Then I set up a loop in which I will run this sum. In this sum, I need to compute xi, like this, and this is the expression. Then I need to compute the function, multiply by delta x, accumulate into a running sum. There it is. And return the result. This is scalar code. With vectors, if I want to do it, for example, with 128-bit SSE for the 2 vectors, this is a legacy instruction set, then all my scalars have to become vectors. For example, dx used to be a scalar. Now I use a function that gives me a vector, and inside this vector I have dx in each of the 4 vector lanes. The running sum, I set it to a vector containing zeros everywhere. Now my loop, look, I go through the same iterations, but I do 4 at a time. So I do fewer iterations than I would in a scalar loop, and this is where my speedup comes from. Okay, here I produce a vector that looks like this: I plus 1, I plus 2, I plus 3, I plus 4. Something that I probably could have missed, but look, in this operation, I is an integer, but we are converting it to a floating point number, so I'm calling a conversion function. Then multiplication, reciprocal square root, another multiplication, addition. I end up with 4 partial sums, and I need to add them all together to return the result. And for that, I use a union. Converter type is a union, which is either a vector of this kind or 4 floating point numbers, depending on how you access it, and it allows me to access the individual vector lanes. It's ugly, it's prone to errors, and it's also not general. What if n is not a multiple of 4? Well, we may need a remainder loop. What if we want to run it on a Xeon Phi, for which SSE is a legacy set? Well, then either swallow a performance hit or rewrite this with AVX-12 instructions. What if we had any memory access? Well, this is where things become really hairy, because with memory access, you may need to worry about how you load data from memory. You need to load from a boundary that is aligned on 64 bytes. for optimal performance. If your data does not begin on a boundary that is aligned, you may need to insert a peel loop. And you may also run into complications with pointer aliasing, and the code may become quite complex. So the vector representations of this simple scalar loop can be numerous and difficult to produce correctly. Thankfully, there is an alternative approach to getting vector instructions in your code, and that is automatic vectorization. With automatic vectorization, you use one of the language constructs that are vectorizable, and the compiler transforms your scalar code into vector code. The language constructs that we are going to study are loops, array notation, and SIMD-enabled functions. So, loops. If you have scalar loops in your applications, most modern compilers will try to vectorize them. I will demonstrate vectorization with the Intel compiler, and I will mention what's different about GCC where applicable. So here I have a full program, but you can see that I have two arrays of length 1024, and I'm doing my favorite operation, a plus b, and printing results for verification. When I compile this code with the Intel compiler, vectorization is automatic. I don't have to do anything. I don't have to set any arguments. The compiler will, by default, try to vectorize code. But if I wanted to see what the compiler is doing, I could optionally indicate qopt report. With this argument, the compiler will produce a text file with the extension opt report, and in this text file, I can find information about what was vectorized in my loop, in my code. I will see blocks like this: loop beginning at AutoVec line 12, column 3. Line 12 is this line. Column 3 is, well, simply because I have two spaces before this 4. Vectorization support, unroll factor. Oh, loop was vectorized. This is what I was looking for. Loop was vectorized is partial success. At least you're running this code with vector instructions. Sometimes you will see loop was not vectorized. Sometimes you will see loop was vectorized, but inefficiently. But it was vectorized inefficiently, and there are things that you can do about it. With GCC, if you are compiling and want vectorization, then one of the two options: either use -O3, the highest optimization level, or use F3 vectorize, I think. I apologize if I gave you the wrong argument, because I think they've changed the name recently. But anyway, with GCC, vectorization is not automatic. Okay, so I told the Intel compiler to vectorize my code. What instruction set did it use when it vectorized? By default, Intel compilers will use a legacy instruction set, so that your code can run on a variety of processors. But this is not what we want in HPC. In HPC, generally, we want to target a specific architecture. And if we want to recompile for a different architecture, we just want to let the compiler do the work. So, with Intel compiler, you will find yourself using -x followed by the code name of the architecture. For example, -x micAVX512 will make auto-vectorized loops targeted for Xeon Phi processors, night planning architecture. Core AVX512 will also use AVX512, but only the modules supported by Intel Xeon processors supporting AVX512. Core AVX512 is for Sandy Bridge, Ivy Bridge, Haswell, Broadwell. I'm sorry, this is actually just for Haswell and Broadwell. AVX is for Ivy Bridge and Sandy Bridge and Ivy Bridge. This is legacy. And if you are going to run on the same machine on which you are compiling, use -x host, and then feature detection will be automatic. With GCC, instead of -x, you use -m, but you have, in the case of AVX512, you have to list all the modules that you're going to utilize. For example, for KNL, you have to list these 4 modules and use O3 or a special flag to enable vectorization. With both Intel compilers and GCC, you can request the vectorization report, and you can also request assembly, which will produce a text file in which you can, and in this text file you can find vector instructions. For example, this is vector addition for packed double precision numbers. And if you find ZMM, this is 512-bit instructions. YMM are 256 and XMM are 128. These are the registers used in the architecture. All right, so the compiler vectorizes code. What exactly does it look like? When the compiler vectorizes a loop, what it will do is it will glue together several consecutive iterations, and what used to be a vector instruction stream will become, what used to be a scalar instruction stream will become a vector instruction stream applicable to a vector containing the scalar data for these 4 or 8 or 16 consecutive iterations. Then, after this vector iteration, it will move on to the next vector iteration. When Intel compiler vectorizes loops, it will only target the innermost loops. So if you have multiple layers of loop nesting, it will only target the innermost. Your loops must have known number of iterations when the loop begins. It is perfect when the number of iterations is known at compile time, because the compiler can pick a great optimization strategy. It is also perfectly fine when the number of iterations is only known at runtime. Automatic vectorization still works. In order for vectorization to occur, iterations must be independent of each other, meaning there should be no vector dependence. Well, it's a weaker form of independence. No vector dependence. I will illustrate it in a minute. And if you call any functions in your loop, then in order for this loop to vectorize, the functions must be CMD enabled. I will explain soon what this means. So far, I've demonstrated only AI plus BI type calculations. And I don't want you to think that this is the limitation of automatic vectorization. It is not. Auto-vectorized loops may be quite complex. Take a look at this snippet. Here I iterate over some range, and this is a snippet of an n-body calculation where I have particle coordinates and I need to compute something like 1 over the square root of xi minus xj squared plus yi minus yj squared plus so on. So there's many variables, and with respect to I, this is a constant. So the compiler will turn it into a vector containing xj in every vector lane. This is not a constant, so the compiler will contain it into a vector containing xi plus 1, xi plus 2, and so on. all of this will become vector instructions. The reciprocal square root will become a vector instruction. If you have vector reduction, well, not in this case, but if you did reduce into a scalar, it is still vectorizable. So auto-vectorized loops can be quite complex. There's another example from this paper where you have particle detection events occurring in a cylindrical detector, and you get coordinates of these events in polar form, phi and r, and you take blocks of these phi and r values, apply the sine function to convert it to the Cartesian coordinate grid, do rounding to an integer, multiplication, this is conversion to an integer, and even histogram calculation can be vectorized on a Knight's Landing process. So automatic vectorization is quite efficient by itself, and it makes your code flexible. But it doesn't feel good to just trust everything to the compiler and have no controls, does it? Well, thankfully, you do have controls. And if you want guided vectorization, then at your disposal are tuning knobs. Of these tuning knobs, the most important one is pragma SIMD or pragma OMP SIMD, depending on which syntax you want to use. Pragma OMP SIMD is actually standards compliant, starting from OpenMP 4.0. This directive you can put before a loop that you want to vectorize, and it will enforce the vectorization of loops. It is useful compared to automatic vectorization when you have SIMD-enabled functions, when you want to vectorize loops that are not the innermost loops, when vectorization fails due to compiler's decision and you want to override this, and where you need to guide the compiler regarding the vector length, reduction, and so on. I couldn't find a good HTML page for the syntax of pragma OMP SIMD, so you can study the syntax of a similar pragma SIMD, which is Intel proprietary. They all support quite a bit of tuning freedom. Here's an example. Once again, the loops don't have to be simple. In this case, this is, by the way, from that heat code library that I mentioned in session 1. It looks like matrix-matrix multiplication, and in fact, here it is matrix-matrix multiplication, but in the original code, we had some code between these 4 loops. And because of that, we couldn't just call a laypack function. But full disclaimer, if you're dealing with a standard mathematical operation, such as matrix-matrix multiplication, don't write loops. Instead, call a dedicated library, such as, in this case, a BLAS library found, for example, in Intel's MKL. MKL stands for Math Kernel Library. It has optimized standard mathematical functions, including basic linear algebra subroutines, optimized for Xeon and for Xeon Phi. In our case, we couldn't do that, so we wrote loops, because there's some extra code between here. Now take a look at the innermost loop. It has how many iterations? 4. By default, this would have been the target for automatic vectorization. And that's not so good, because if we are doing calculations on Xeon Phi, then in single precision, vectors are (16) wide, with only 4 iterations. When the compiler glues together iterations of the inner loop, we could at most use 1/4 of the vector. So we would be losing a lot of cycles. Another reason why vectorizing in I would be a bad idea is this. What it gives me is strided access. Remember I showed you this diagram where the workflow of the vector calculation is to first load data from memory into registers. So how do you do that? Well, if you glue together several iterations in I, then this will be the same. So this is a constant. This gives me unit stride access, meaning that for consecutive values of I, I'm accessing contiguous memory locations. So it's a contiguous block of data that I would have to read or write for multiple values of I. But here, the story is very different. I'm multiplying by n, and n is 128. So I'm reading one element here, skipping a lot of elements. Reading one element here, skipping a lot of elements. Reading an element here, skipping a lot of elements. And I'm trying to put the results into a small contiguous vector. Because of the built-in parallelism in memory architecture, whenever I access one element, the memory actually sends me a whole cache line with its neighbors. I'm discarding these cache lines, therefore not using the memory efficiently. So, bottom line, bad idea to vectorize an I. But I want the loop in I inside because of the memory access pattern. This is why I'm using Pragma OMP SIMD above the K loop. It will force K loop vectorization and disable I loop vectorization. K is a good idea because K ranges from 0 to n, so n is a multiple of the vector width. With respect to K, this is a constant, this is unit stride, and this is also unit stride. Well, here is guided automatic vectorization. I'm not happy with automatic vectorization, so I provide the compiler with some guidance with regards to what to use. Another form of language constructs that is conducive to automatic vectorization is array notation. If you are a Fortran programmer, then you probably know expressions like this. This is Fortran array notation. In this notation, I can specify slices of arrays. This is start, this is end, and this reads copy n elements from 0 through n from array B into array A. In C, this is not a part of the language, but there are language extensions for array notation supported by the Intel compilers, and also by GCC, starting from, I think, version 4.9, or some later versions do use it. You have to just be aware, if you're coming from Fortran, that the syntax is different. The first argument, well, instead of round, you have square parentheses, and the first argument is still start, but the second argument is not end, but rather it is count. So here I'm adding 16 elements from B, starting from 32, to 16 elements of A, starting from 0. You can indicate the third argument, which would become a stride. You can specify multidimensional arrays, and you can even omit the range if the compiler knows the range syntactically. Array notation is definitely a replacement for loops. It is a shorthand for loops, for sure. We have seen cases where array notation is also an optimization method. This was particularly true when we had an application with strided memory access, when the stride is different in the left-hand side and in the right-hand side. You can read the paper here. And it implements the Kulitzaki method for fast Fourier transforms in the case of huge one-dimensional arrays. And at the bottom end of the spectrum for small arrays, it uses MKL. The nature of the Cooley-Taki method is to take a large array and then pick out every other element from this array and stick it into another contiguous array. So by nature, you will have stride 2 in the right-hand side and the left-hand side, or the other way around. So what we saw is when we implemented this with loops, it worked slightly slower than when we implemented this with array notation. It shouldn't be like that. Maybe it's different in the latest compilers, but that's what we saw back then. Finally, in addition to loops and array notation, you have SIMD-enabled functions to express vectorization opportunities. SIMD-enabled functions are functions that obey certain rules and that are declared with a declaration like pragma omp declare SIMD. These functions are ready to be used in a data parallel context. For example, my simple add, I can declare it as SIMD enabled, and the compiler will produce 3 versions. One of them is scalar, another is vector, meaning that its inputs are vectors and the output is a vector, and the third one is masked vector. Then I can call this function from a SIMD enabled, from a loop that gets auto-vectorized, and the compiler will be able to pick out the correct vector version from the object file and vectorize my loop. It is not always necessary to use SIMD-enabled functions. For example, if the declaration of the definition of the function and the usage of the function is in the same source file, then the compiler can just inline them. And it's not necessary to go through SIMD-enabled functions. SIMD-enabled functions are useful when the definition of the function is in one file, but the usage is in another. For example, when you're building a library. When you are building a library of functions, you do not provide your source code to the user by default. Instead, you provide an object file or a library file, and the user is supposed to pick out the right functions from that file. SIMD-enabled functions help here. And just like array notation and auto-vectorized loops, SIMD-enabled functions are not limited to A plus B. They may be quite complex. This is from another paper where we demonstrate SIMD-enabled functions with using as an example error function calculation using an analytical approximation. As you can see, it takes a single scalar input, but what happens to the scalar input is tremendous. Absolute value, some expression, transcendental function calculation, exponential computation, copy sign. All of that can be applied to short vectors element by element. And the compiler will know how to translate this into vector instructions. It will know that this is a constant. It will know to use temporary constants here. It will know to reorder operations in such a way that you fill the pipeline more efficiently, and so on. So this is the quick introduction into automatic vectorization. I will show you a couple of additional controls before we take a break and move on to a practical demonstration. When you are working on your code, trying to vectorize it, you want to see in the vectorization report, loop was vectorized. When you see it, this is at least partial success. It is partial success because there may be more that you can do. Also, sometimes you will see that the loop is not vectorized and there is no clear explanation why. Or there is an explanation, but it doesn't make sense. So I will try to make sense of the possible explanations for non-vectorization and of the possible red flags that you can look for in the optimization report. Things you cannot vectorize. You cannot vectorize loops with true vector dependence. For example, in this case, we're going in I from 1 to n, and a of I depends on a of I minus 1. This calculation has true vector dependence. I have to know a I minus 1 before I can compute a of I. If I glue together several iterations in I and perform them together, I will not get correct results. By the way, in contrast, this is safe to vectorize. If I have to know a of I plus 1, and I'm guaranteed to go from left to right, this is safe to vectorize. Interestingly, it is not safe to vectorize in GPUs because you're not guaranteed in which order you will visit different values of I. With Intel architecture, you're guaranteed to go from left to right. Then this. I need to know a of I minus 16 before I can compute a of I. This loop may or may not be safe to vectorize depending on the vector length. If the vector length is 16 or less, then there is actually no vector dependence. It is safe to vectorize. But if the vector length is longer, for example, well, there are no architectures, no Intel architectures with longer vectors, but if you do loop unrolling and treat unrolled loops as one iteration, then you need to be careful here. Because of these limitations, the compiler will sometimes refuse to vectorize your loops. Here's a function. It copies array B into array A, or so it looks. To us, it is A equals B, but to the compiler, there is an ambiguity. If A and B are not aliased, meaning that A and B are pointing to different memory locations, then indeed it is a memory copy and it is safe to vectorize or use a memory copy function. But what if somebody smart calls this function with something like A and A minus 1? Then what we're doing here is A of I equals A of I minus 1, and this is vector dependence. In order to compute this correctly, either you do scalar computation or you do 16 scalar iterations and then proceed with memset, basically. The compiler, looking at this code, may do one of the two things: refuse to vectorize or implement multiversioning. Multiversioning will be reflected in the optimization report like this: version 1 vectorized, version 2 not vectorized. It means that the compiler implemented two code paths. One code path will be taken if the pointers are not aliased. The other will be taken if pointers are aliased. And at runtime, the code will check which path to take. This is convenient because your code is general. But the flip side of that is that if you start this loop very frequently, the loop is short and you start it frequently, then the check for aliasing can take a significant amount of time. So this is a red flag for vectorization, for optimization, that you may want to eliminate. To eliminate multiversioning, you can use IVDEP, pragma IVDEP. This directive performs pointer disambiguation. It means that it promises to the compiler that there is no ambiguity. All pointers are pointing to their own memory locations in the entire loop. And then multiversioning will be dropped and the loop will be vectorized. Sometimes this is enough if the compiler refuses to vectorize the loop completely. By the way, in addition to pragma IVDEP, there is also keyword restrict, which applies to a single pointer, promises that it is not aliased with any other pointer. So this is these are the essential controls for vectorization that you have. And I have a cheat sheet of vectorization directives. All of these are clickable. download the slides, and click away. PragmaOMP CMD enforces vectorization of loops. PragmaVector always makes the compiler vectorize loops, even if the compiler thinks that the vectorization is not profitable. PragmaVector aligned promises that all memory accesses begin on aligned boundaries. This is the same for a single pointer. PragmaVector non-temporal, we will talk about it again in session 10, uses streaming stores, useful for avoiding cache pollution and maximizing bandwidth to memory. Pragma no vector prevents loop vectorization. IVDEP, useful, for example, to study the speedup that you get from vectorization, or to prevent vectorization of loops that have branches that are rarely taken. A Pragma IVDEP is pointer disambiguation, restrict qualifier the same for a single pointer. Pragma loop count promises to the compiler that at runtime there is at least, at most, or on average so many iterations. This helps the compiler to pick a good vectorization path. With all of these tools, hopefully you can achieve loop was vectorized. This statement in the optimization report. What do you do now? We will revisit vectorization in session 7, and we will see how you can take code that's already vectorized and improve its performance by changing data containers so that you have unistride access, doing data alignment, padding multidimensional containers, eliminating peel loops with directives, eliminating multiversioning. But the last point I highlighted in bold. The most important thing you have to do for your vectorization is to optimize data reuse in caches. The truth in modern architectures is that vector arithmetics is cheap. Memory access is expensive. So, if you don't optimize cache usage, vectorization will not matter. You will be bottlenecked by memory access. You can vectorize and optimize all day long, but if your data is coming from the main memory, this is what you will spend your time waiting for. Vectorization makes vector arithmetics just too cheap. So, the key to unlocking vectorization, the key to unlocking the performance of vector calculations is actually optimization of memory access. And we will talk about this in great detail in session 10. So stay tuned. This is the most important aspect. If you can do math instantaneously, but if you have to wait for data to come from the main memory, there's no use. Well, that is my theoretical part of the presentation for today. We talked about vectorization. It is enabled at the default optimization level in Intel compilers. You can use loops, CMD-enabled functions, and array notation. You can see what happens inside of your code using QOP report. And later in the course, we will revisit vectorization from the point of view of performance optimization. I do have a practical exercise planned. And as usual, this is a 2-hour webinar. After a 5-minute break, we will resume for a practical demonstration of vectorization on Intel Xeon Phi processors. So stay tuned and talk to you in 5 minutes. Muting my microphone. So let's resume. As promised, a hands-on demonstration of automatic vectorization. Let's see what vectorizes and what doesn't. To play with automatic vectorization, in House Series Labs, we can find Lab 301. There are two source codes inside. Inside vectorization CC, there is a little code that declares two arrays, initializes them, as you can see, using array notation, does my favorite a plus b, then does my favorite a plus b in another way by calling a function, and also calls a function with a vector loop inside. To compile this code, we can just run make, and you can see that it does a lot of compilation. It compiles vectorization CC and worker CC first with the argument xavx. So this will be for an Ivy Bridge processor. Then the same is compiled with the argument -mmic. So this is for a Knight's Corner architecture Xeon Phi coprocessor. And for the Knight's Landing architecture, xmic avx512. In all cases, I request an optimization report, and the optimization report file actually contains the architecture inside of it. This compilation produced an executable. I can run it on the login node, and it does nothing. It's supposed to do nothing because we are not really going to focus on performance. We will focus on performance in session 7. We are going to focus on what's happening inside the vectorization report. And believe me, it is going to be very entertaining. So let's open, how do I do this? I guess like this. Let's open the vectorization report. Yeah, how about like this? How about vectorization report for Knight's Landing? What do we find there? Well, this is a text file, first of all. And there we find blocks, just like I showed in the slides, loop was vectorized. So this pertains to the loop in line 16, which is this one. So initialization was vectorized. You scroll down, you find that there is a remainder loop that was vectorized. Interesting. Then the next one is in line 20. So quietly, the compiler actually fused these two loops into one. This is why we don't see anything in regarding line 17. Line 20 loop was vectorized, and again the remainder was vectorized for that one. Line 24 loop was not vectorized because a loop with function calls is not considered an optimization candidate. And there is nothing about the next line because there's no loop. Okay, what I want to see is how much can I change this code before the compiler gives up and refuses to vectorize what I've written. Let's play with this code. Well, I've already said that some calculations cannot be vectorized. For example, if I put b of I minus 1 instead of b of I, this would be a problem. So how do I recompile? How about this? Recompiled. Line 20. Loop was not vectorized. Vector dependence prevents vectorization. Assumed flow dependence between b of I and b of I minus 1. So this is what you see when there is no vectorization. If I used b of I plus 1, that vectorizes. Ooh, wrong key. Okay, reread the vectorization report. And the loop is vectorized once again. How about we introduce some constants? And to save time, I will complicate it quite a bit. How about also the math library? And what about something like this? And what about temporary variables? To be nice, maybe I need to do this. How about a stride? Let's see if this vectorizes. Wrong. So the loop is in line 21. It was vectorized. So this is interesting that it gets vectorized despite non-unistride access, despite transcendental functions, despite temporary variables, constants. This is all not a problem. Let's investigate what this remainder loop is about. And to do that, I will go and edit the make file. In the make file, I will change qopt report to qopt report equals 5. This will give me more verbosity. So, recompile. And look for the loop in line 21. As you can see, now I have quite a bit more information. For example, the compiler is assuming that b of I in line 23 has aligned access, but b of I plus 1 has unaligned access. Same for A. It reports non-unistride loads, and this is because of the stride here. Consecutive values of I map to strided memory locations, and non-unistride load is a red flag in some cases. It also reports a vector length of 8, which is correct for 512-bit vector registers and double precision numbers. But here, something important. Unroll factor is set to 4. Unroll factor setting to 4 means that the compiler in the assembly unrolls 4 vector iterations. I will show you assembly in a second, and it's very interesting why and how it does that. But this is a piece of knowledge that would be very difficult to guess from just reading the documentation. This unrolling is, in fact, an optimization measure, and it has to do with well, not incrementing the loop counter too often, and also I believe it has to do with utilizing more of the register file. Scalar loop cost, vector loop cost, estimated potential speedup. And also this unroll is the cause for loop unrolling, for remainder. So let's do this math. N is 10,000. 10,000 divided by 8 is, I know this, 1250. So if we did a single vector iteration, and then another vector iteration, and another vector iteration, we would do 1,250 vector iterations. But we are unrolling by a factor of 4. So now 10,000 divided by 4 times 8, the number of unrolled iterations is 625, 312.5. Not an integer. Meaning that we don't have an integer number of unrolled iterations in 1000. So what the compiler will do is it will perform 312 unrolled iterations plus another 8 by 2 for a total of 10,000. But those last two will be executed in a separate loop. That separate loop is extra code, but it pays for itself by utilizing more of the register file. So let's see what the compiler does inside the code. I can just take this command and I will repurpose it. So instead of compiling like this, I will compile with dash capital S. And now this file actually contains assembly rather than binary code. The assembly is difficult to read, but thankfully there are hints. So this comment at the end is the line number and the column number to which it refers. So let's look for line 21. And there it is. So this is the beginning of the loop. You can see that there's vector broadcast, I suppose, of this. And then this is a vector load. It uses a load for packed single precision operations, single precision data that doesn't really matter. Load another one, compare. Is that what I think it is? Where does the math start? Permutation. Yes, so it is not trivial. As you can see that there's some permutation going on. I suppose to shift this vector to be able to apply the operations to it. The compiler detected opportunities for fused multiply add. And there's so many of everything because it is an unrolled loop, and the compiler ordered the operations to minimize bubbles in the pipeline. Here's my square root. This is also a vector instruction. And the square root is actually followed by something interesting. There's scale, fix up, IMMPD. What's happening here is the square root, the result of the square root, is patched to improve its accuracy. I believe it is patched to handle denormal numbers. So a lot of things that I would have no idea about doing if I was writing it by hand, and the compiler thankfully performs what it needs to. Another interesting aspect is that if instead of the square root I had something like an exponential, is instead of, because there is no, well, how about logarithm? Because there is no vector instruction to compute a logarithm in hardware, the compiler will actually call a different function. And this function comes from the short vector math library. Let me search for it. Yes, so this is my logarithm. Instead of calling, like in that case it did vector sqrt, here the compiler calls the log function on 8 numbers from SVML. SVML stands for Short Vector Math Library, and this is a library that becomes available when I use CMath. I'm using the Intel implementation of it, and as you can see, I'm calling a function, but the loop still gets vectorized. This is because that function is SIMD enabled. So I have been using SIMD enabled functions, and I have been using automatic vectorization possibly without knowing them. But it is useful to know what's happening so that I can tweak how vectorization works. For example, if I have my own function that is supposed to be SIMD enabled, what do I do to make it SIMD enabled? Because if you take a look at the optimization report for line 27, it says loop was not vectorized, loop with function call is not considered an optimization candidate. And indeed, this function is not in this file, so the compiler cannot just inline it. This function is in worker.cc, and there it is. And if I look at the optimization report for worker.cc, not much more fun. My scalar add worker.cc, that's that. Nothing else. Some information about register allocation. Not exciting. And the whole file is The whole file is 2.1 kilobytes in size. Let me declare this function SIMD enabled so that I can use it in a data parallel loop, in a data parallel context. Pragma OMP declare SIMD is all I have to do. The compiler will recognize that this function needs to be compiled 3 times. So when I recompile it, the only catch is that when I recompile, I have to use the argument qopenmp. So in the make file, I have to edit use -qopenmp. Let's try again. So recompilation succeeded, and now if I take a look at this file, instead of 2.1 kilobytes in size, it is 2.4 kilobytes in size. So something happened when I added pragma OMP declare SIMD. And exactly what happened is described in the optimization report, obviously. Now I will have several implementations of this function. One is called myscalar add x n2vv. Another is called, let's see what it's called, xm instead of n 2vv. And there's one more just called myscalar add, I think. Yes, there it is. What are these 2 additional functions? They are, as the name suggests, vectorized versions of this function. For example, myscalar add x and 2vv. What it does is it accepts XMM vectors, vector length 2. I honestly don't know why 2. I suspect this is a compiler bug, but it works as expected. It is a bug of reporting, I suspect, but it should have been vectorized with ZMM. So formal parameter types are vector and vector. So instead of accepting two scalars, it will accept two vectors. And the same for return type. The M2VV is the masked version of this function. It is masked. And it allows you to set or unset some of the to set or preserve some of the output values. Okay, I made my function SIMD enabled. Let's go back to vectorization.cc, recompile it. Oh wait, before I recompile, I have to tell it, right? I have to tell it that the signature of this function has changed. So I'm going to go here and also insert here pragma omp declare SIMD. Okay, so it's recompiled, and let's check vectorization report. We are interested in the loop in line 28. This is where the SIMD enabled function was. In line 28, now the loop is vectorized, and the compiler reports vector length 8, because the function call here was found with SIMD length. So it found only the XMM version of this function. So maybe there's something that we need to add to make it vectorize with ZMM. And there is actually an argument of this function. I don't want to go there right now and experiment, but I think there is an argument of this function indicating the desired vector length. Although it's strange that it doesn't pick up ZMM from xmike vx512. Well, that's our experiment with SIMD enabled functions, and we have one more place where we can experiment, and this is a call to a function to which we pass two arrays, and the function itself is in a different source code file in worker.cc. So let's see what we have in the optimization report for this function. I'm doing something completely vectorizable, a plus b. What does the compiler think about it? This loop is in line 7, and the compiler multi-versioned this loop. Version 1, the version 1 has a p loop, a main loop, and remainder loop. And then there's also version 2, which is not vectorized, because this is the non-vectorizable loop instance from multi-versioning. This is all good, because it makes our code general. Whether or not our user is honest and passes unaliased A and B, or maybe they pass B equal to A minus 1, in which case we have true vector dependence, the code will work and it will work correctly. But what if we wanted to get rid of all of this code that we never take and promise to the compiler that we always have non-aliased pointers? We could do pointer disambiguation, And the tool that I showed during the presentation is this directive, pragma ignore vector dependence, ivdep. So the loop was already vectorized. This pragma just removes unnecessary code from the vectorized version. I keep pressing the wrong button. About this. Recompile. Reread. Now, loop in line 8 is still vectorized. There's still peeling. There is still remainder, but no multiversioning. Multiversioning is gone. This is convenient. And what if we could guarantee that A and B always begin on boundaries that are aligned, and therefore the peel loop and the runtime check for peeling is also not necessary. It will reduce the file size, and it will also eliminate one runtime check, so it will lower the overhead of this loop setup. We could use pragma vector aligned and recompile. And reread. The loop is now in line 9. And we still have the main loop and the remainder loop, but no peeling. Right? If I go up, there's no peel loop. It was eliminated, and both of these directives are promises. We promise no aliasing. If at runtime the promise holds true and there is no aliasing at runtime, then we are fine, and the code will run slightly faster. It will produce correct results. But if we actually give it aliased pointers, then we will quietly produce incorrect results. There will be no error, no warning, no crash, just incorrect results. So dangerous. Pragma vector aligned, depending on the architecture. If you don't provide aligned pointers, you can either just run slightly slower, or your application may crash with a segmentation fault. This happens particularly for Knight's corner architecture. We will talk more about alignment in session number 7, and we will see how alignment can be provided with special allocators, with multidimensional array padding, and also with the padding of loop bounds. So this was my little exercise for vectorization. Feel free to dig around more. I'm sure you can try to confuse the compiler in a variety of other ways. We will wrap up. And tomorrow, in the session about multithreading, we will talk about another form of parallelism, task parallelism, and OpenMP as a framework for multithreading that can help you to achieve code portability and future-proofness. Thank you very much for joining us today. I wish everybody a great rest of the day, and see everyone tomorrow. Goodbye.